Greetings from EPG Pathshala. In this module, we are going to discuss about stream cipher, block cipher and Feasel structure. Up till now we have seen simple substitution and permutation, and we found that no scheme is as powerful as it cannot be broken by cryptanalyst. In this, we will talk about Feasel structure that suggests how to make the cipher unbreakable. That means add more substitution, more permutation, add number of rounds, so that structure is so complex that no analysis can break the cipher. I would start my discussion with stream ciphers. Stream ciphers take one bit or one byte at a time from digital data stream and encrypts. For example, we saw Varnam cipher in the previous module. What it did? It took one bit out of the plain text, one bit out of the key and generated a ciphertext. So, Ci equal to Pi exclusive OR with Ki. Block cipher, block of plain text is taken at a time and ciphertext block is produced. Block length is usually of 64 bits or 128 bits. Block cipher processes plain text block of n bits to produce a ciphertext of n bits. For example, 4-bit plain text 1011 is taken, the ciphertext generated is 1100. The observation you have to do here is the length of the plain text and ciphertext is same. Block cipher, block size 2, then 2 raised to n possible plain text are there. Look at the table 1, the plain text and corresponding ciphertext is given. Plain text 00011011. That means the length of the plain text is 2, so combinations are 4. 4 combinations of 2-bit plain text are generated and their corresponding ciphertext are given in the table. What is the difference between table 1 and table 2? So, table 1 has a mapping and table 2 has a mapping, but the observation is in the table 1 there is unique 1-to-1 mapping between plain text and the ciphertext. In table 2, for plain text 00 and 01, the ciphertext is 11. So, table 1 has a reversible mapping. So, from the ciphertext also there is 1-to-1 mapping to the plain text. So, given ciphertext we can generate the plain text, but in table 2 for the ciphertext 11 there are 2 corresponding plain text. So, it is irreversible mapping. For our encryption scheme to work, it should be reversible. The next question is, what is Feasel's ideal block cipher? So, check the table and what you can observe is we have a 4-bit of input text. So, the combinations are 16. So, for all the 16 combinations we have unique 1-to-1 mapping. So, 4-bit input, there are 16 possible inputs mapped with 16 possible outputs. 16 possible outputs are again represented by 4 ciphertext bits, referred as ideal block cipher. Why this is called ideal block cipher? Because it allows plain text ciphertext mapping for all possible inputs. What are the problems with Feasel ideal block cipher? If you have observed, ideal block cipher is like a substitution cipher because for each possible input there is possible output mapping. As the block size is small, it is vulnerable to statistical analysis, saying that if it is only 2-bit input for each plain text, the attacker has to try only 4 combinations. For large block size, ideal block building implementation and ideal block storing is infeasible. For 4-bit inputs, there are 16 rows generated. So, required key length is 4 bits into 16 rows, that makes 64 bits. In general, for n bits, n into 2 raised to n bits are required. To prevent statistical attack, block length of 64 bits must be there. So, it requires 64 into 2 raised to 64 bits. If we go into the detail of Fizzle cipher, block cipher with a length of k bits and a block length of n bits. So, there are 2 raised to k possible transformations, not 2 raised to n factorial. Why? Because our key length is of k bits. So, Fizzle suggested to use substitution and permutation alternatively to produce the ciphertext. We have already covered substitution means each plain text element is replaced by a corresponding element. Replacement is unique. When we talk about permutation, the order of plain text element is changed. Fizzle cipher suggests confusion and diffusion for purpose of suppressing the statistical analysis. To go ahead with the discussion of diffusion, it says each plain text digit affects the value of many ciphertext digit. For example, our message M is made up of M1, M2, M3 up to Mn characters. What diffusion says, take k successive letters, add them all together and get a modulo 26, and this would be your cipher character. What it says once again, if you want to get a ciphertext for the first character, and if we keep the k successive letters k to be 3, we have to add M1, M2, M3, get a modulo 26, and that would be a ciphertext character for character 1, that is M1. So, C1 depends not only the characteristic of M1, but it depends on M1, M2 and M3. So, statistical relation between plain text and ciphertext is so complex that it is difficult to derive key. Now, the next it suggests, Fizzle suggests confusion. Confusion is the statistical relationship between ciphertext and encryption key is so complex that it is difficult to derive key. Confusion is achieved with the use of a complex substitution cipher. So, diffusion and confusion, both terms are clear. So, let us look at the slide to check the Fizzle cipher structure. What is the observation from the structure? That we have a plain text of 2W bits. It has to be divided into 2 equal halves. So, each half would be made up of W bits. We will call it L0 and R0. The structure says round 1, you apply function with the key and the right half of the input, right half of the plain text as input and generate an output. exclusive OR with the left half of the input and get the output that would be the right half of the first round. Right half of the 0th round should be copied to the left half, and that would generate the left half for the next round. If you are still not clear, check on the slide how the Fizzle cipher works. Input is plain text block of length of 2 W bits. The key is K. The procedure says, as I explained, divide your plain text blocks into 2 equal halves, that is called LE0 and RE0. As Fizzle suggested, perform more number of rounds so that the relationship between plain text, key and ciphertext is so complex that no one can derive it. So we need to perform n rounds and combine to produce the ciphertext block. Each round I has inputs L, E I minus 1 and R E I minus 1. Suffix I minus 1 suggests that the left half is taken from the previous round. RE I minus 1 suffix I minus 1 suggests that the right half is also taken from the previous round. When you are talking about ith round, RE and LE would be taken from the previous round, but key would be taken of the current round, that is ith round. Apply a round function f to the right half, that is called RE I minus 1, take output an exclusive OR with the left half and substitute it with the right half, that is called REI suffix I. LEI will be substituted by RE I minus 1 suffix I minus 1 suggests previous round. So clear, left half of the new round is nothing but a direct substitution of the right half of the previous round. Mathematically we can write as LEI equal to REI minus 1 and REI, that is right half for the current round, equal to LEI minus 1 exclusive OR with a function REI minus 1 and KI. Output of the nth round LEN appended to the REN, that is the output of the nth round would be appended together, and then to get the final ciphertext we need to perform permutation. Yani for the final ciphertext, the right half of the nth round would go in the left half and left half of the nth round would go to the right side. So it says REN appended to LEN. That gives you the ciphertext after nth round. So you have observed that the structure is so complex. Let's evaluate the strength of the Fizzle's network. Strength of the Fizzle network depends on few parameters. The first is the block size. Larger the block size, more the security, but operation takes longer time. Time increases. Key size. Larger the key size, more the security. Once again, time taken would be more. Number of rounds, more security. Sub-key generation algorithm, complex the algorithm, difficult for cryptanalysis to generate the key. Round function f, it is a complex function. As the complex function is used, greater the resistance to cryptanalysis. Idea is, if you are working on the Fizzle cipher, you need to work around all these parameters so that you can build a cipher with greater strength. If you observe the decryption It is exactly the reverse process of encryption. In the decryption, the input would be the ciphertext. Once again, they would be divided into two equal halves. In the slide, we have shown 16 rounds. So, after 16 rounds, we have generated RE16 and LE16, that is our ciphertext. So, in the decryption, the first would be RE16 as a LD0. LD0 suggests the left half for the first round of decryption. RD0 is nothing but a right half for the first round of decryption. RD0 would be LE16, यानी left half of the 16th round of encryption. Now exactly we have to do the reverse process. What is observed from the figure is right half where the function is applied, it is exclusive OR with the left half to generate the next round of right half of the decryption, which is nothing but the left half of the 15th round of encryption. The same way we have to copy the left half as it is to produce the right half. So, observed, it is very complex but exactly the reverse process of the encryption. At the end of the decryption after 16 rounds, what will be generated? It would be RD16 and LD16, that is nothing but LE0 and RE0 appended together to get our plain text back. Fizzle cipher structure decryption. For decryption, input is the ciphertext block of length 2W bits, key, subkey Ki in reverse order. So, if we have applied K1, K2, K3, K16 in encryption, in decryption K16, K15, K14 to K1. Assuming that 16 rounds are performed, the general structure is LDI equal to RDI minus 1. We are talking about decryption. And RDI equal to LDI minus 1 exclusive OR with the output of the function applied on the RDI minus 1 and Ki. It's clear, I minus 1 yani taken from the previous round, I yani taken from the current round. Feasel cipher structure has 16 rounds, very obvious. Ith round encryption is denoted by LEI appended with REI, and 16 minus ith decryption round is denoted as LD16 minus I appended with RD16 minus I, which is equivalent to REI appended to LEI. Then comes two types of cryptanalysis. First is a differential and second is linear cryptanalysis. Differential, as its name suggests, we are taking the difference of whom? The two messages. For example, you are given two message MI and MI dash. If we want to find out in how many characters do they differ, simply do exclusive OR. That would give you delta M. So, delta M with a suffix I is nothing but exclusive OR of MI with MI dash. Now, if we want to find out delta MI plus 1, what are we going to do? MI plus 1 exclusive OR with M dash I plus 1. MI and MI dash, MI plus 1 and MI plus 1 dash, they are nothing but differing in some bits with each other. So, what an attacker has done? Attacker has tried to produce a plain text similar to the which was transmitted, but not exact plain text, just he has tried to produce the similar plain text. So mi plus 1 is nothing but mi minus 1 exclusive OR with output of the function mi and ki. As our formula suggests, exclusive OR with m dash I minus 1 exclusive OR with the function of mi dash and ki. So if we do exclusive OR of mi minus 1 and mi dash, it gives the same value mi minus 1, which is exclusive OR with function output of mi and ki, exclusive OR with function output of mi dash and ki. What is the conclusion out of this discussion? That for the same subkey, many pairs of inputs to f with the same difference yield the same output difference. So if delta mi minus 1 and delta mi are known, the probability that we can produce delta mi plus 1 is high from the equation. If many such differences are known, subkey used in the function can be determined. This was about differential cryptanalysis. Now we have to talk about linear cryptanalysis. As its name suggests, for linear equations we have to use a1, a2 up to an, that is those are plain text characters, b1, b2 up to bn, those are cipher text characters, and we have to generate k, that is c1, c2 up to cm. Plain text and cipher text characters are exclusive OR. Plain text and cipher characters are n bit long and k is m bit long. Evaluate p exclusive OR with c for large number of plain text and cipher text pair. If that exclusive OR operation results in 0, that means key used is all zeros, and if it comes to 1, that means key k is all ones. So this is how we can use cryptanalysis, linear cryptanalysis to generate the key. Fizzle cipher was based on block cipher. So if we want to design block cipher, there are 3 parameters that can be worked upon: number of rounds, function f, and key generation. These are the 3 important aspects of design of a block cipher. The first, it said number of rounds. We have already emphasized more number of rounds, it is difficult for a cryptanalytic attack. Even if function f is easy to break, more number of rounds make the cipher more secure. Function f design. You have it in mind, when we used Feasel structure, we applied function f. F must be difficult in what terms? In terms of evaluating through linear equations. F must produce avalanche effect. I introduced a keyword, that is avalanche. Avalanche is nothing but it says if we change one bit, it makes a cumulative effect of change in many bits. F must follow bit independence criteria. Bit I is inverted for any I j k, then output bit j and k should be changed independently. J and k should not depend on each other. When we are designing block cipher, there is third criteria, that is key generation. Generate one subkey for each round. Subkeys should be derived in such a way that individual subkeys cannot be determined. Reverse way, from subkey one should not be able to derive the main key. So in this module we have evaluated the strength of the block cipher. We can increase the strength by using Fizzle. Fizzle structure emphasized on more number of substitution and more number of permutations. More substitution permutation used, the scheme becomes complex, but definitely it takes more time to encrypt and decrypt. The design of the block cipher depends on 3 parameters: subkey generation, function f and number of rounds. So in the next module we will check how to encipher the DES algorithm.